Okay. Where was I? I made this LIN network. Over to the microcontroller. Hold on. So, just bringing up my documents. And our master ECU will evolve. So we won't just have a LIN transceiver. We'll also have a CON interface. I should maybe write like this. Interface. And an Ethernet interface. Because we're just assuming that it's going to do everything. It's going to be a controller of anything in the vehicle. So in this network, we might have a couple of more network buses or interfaces. So right now we have power management, core, which is just the DC-DC and another DC-DC. And then the microcontroller with the debug interface, crystal, just decoupling capacitors, pull up resistors, pull down, and nothing else. Actually, I don't think this has an Ethernet interface, so that's maybe my first mistake of including that, but maybe we can add a Mac controller or something. Let's or upgrade the MCU. Yeah, let's say we only need a CON interface then, for now. And let's say CON will be the main interface to other more heavy duty ECUs. Where we need to send more data than what we can on a LIN interface or on the LIN bus. And I think we go NXP still. Why not? Can go to network. CON interface CON LIN. USB, TI. Microchip. Here we have CONF-D as well. Flexible data rate, so we're able to send more data. Should we maybe stick to a simpler one for now? The small outline IC with 14 pins, maybe. Start there. Here's just different package. Oh, it's also a high speed CONF-D apparently. Takes 5 volt in. Check this one as well. Yeah, here we have some example circuits, or an example circuit here. We should follow this one, which I think we already looked at one time. Yeah, or no, it was for the LIN transceiver. Yeah, and this document is available, which is nice. It's really nice. It got everything, explaining how it works, hardware application, the termination resistors. Well, let's go for this one in this package, and then we can switch to this package later on, just to try this type of package. So we have CON, power. Oops. Oh. Split. we're evolving. We can't just, we just have to keep going and add stuff, which I think is fun. Hardware application and common pins. This is basically going through main features of every chip, and we're using the TJA 1043, 43, this one. Can look through it real quick. And we're using this package. It'd be able all time clamp 30. Even when the internal IO and VCC supplies are switched off. Normal, listen only, standby, sleep, and go to sleep. Should actually so if anyone is joining in, wait, can you see this now? Oh, okay. So in level 2, it's in sleep, VCC supply is off, microcontroller is unpowered, node power consumption is very low, level 1, the bus is in standby or the transceiver is in standby. There is voltage on the VCC supply, microcontroller is powered, and it's in a low power consumption stage. And here's a hardware application. Figure 30 shows how to integrate TJ 1043 within a typical application. The application assumes a 3 volt supplied host microcontroller. There's a dedicated 5 volt regulator supplying the transceiver, a dedicated 3 volt regulator supplying the microcontroller. Right. So a 3 volt to the transceiver and then a 5 volt to the 5 volt to the transceiver, 3 volts to the microcontroller. Okay. I mean, we can just take, not this, the 5 volt here, and a 3.3 volt here. Yeah. Because what else? We have to think about this. What else is on this 5 volt here? Currently nothing. It's just supplying this LDO, and this again is not used anywhere except the microcontroller, which is on a 3.3, just according to this diagram. But then we have to get a 5 volt, which we also have. It says a dedicated 5 volt regulator. What are we doing with this? How much is it consuming even? Could just get a low low cost LDO also for this if we're not really consuming anything. How much is it consuming? Maybe I check the datasheet for that. Supply current, maximum 65 milliampere. I wonder if we can just add an LDO to step down 12 volt here. Without it having any like thermal problems. I mean, we're not consuming that much. LDO. $35 to like a linear. Fixed output 500 milliampere in your LDO regulator. Okay. Yeah, okay, that one is too low input range. This is a 1048. Hardware application. Here. Yeah, let's just take the 5 volt from here. So we can also take away. So plus 5 volt. For example, 47 nanofarad. Let's just see what it says. So we take the power supply pins first. Better supply ensures local and remote wake up capability of the TJA 1043 when the VCC supply is switched off during sleep mode. Nevertheless, the current consumption at this pin is very low. Recommend to place a series resistor, for example 1 kilo ohm, into the battery supply line of the transceiver for enhanced protection against automotive transients, given the max supply current. I'm bad though. Okay. Transient protection. So what they want is a resistor. Just steal one from here. Then a capacitor. Form a low pass filter. So that's the VBAT in 10 nanofarad and 1 kilo, for example. But we'll just We'll work with the examples now, and then we'll see. Oh wait. So this needs to be on the battery. The 12 volt actually. And then if we wanna wake it up better externally. Wait. Or how is it? Onto the wake pin. Won't be that pretty. I usually like to edit the symbol and orient the pins so it's a bit more logical. It has a nice flow. It looks better. But sometimes you have to just get on with it too. You can't have it perfect all the time. And if you enjoy electronics, you'll still be able to learn and read a schematic without any issue. So, did we include a button in a different one here too? No. Here maybe. No. Let's say that we will add a switch, a single pole, single throw, single pole, single throw switch. Switch. Da, 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 da. Separate same symbols, okay. For example, 2.7. Pin ERRN is a push-pull output state for signal failure conditions to the microcontroller. It is typically connected to an input port pin of a microcontroller. So we can assume that it's just leaving this page and going to the microcontroller. So we can place a hierarchical ugh, I can't even ERN H MCU EERN. So output stage, push-pull output stage. So here it's an input. And here then it's an output. STB. More information on this is given in chapter 6.4. During sleep mode, it is floating due to the typical pull-down behavior of the input pin of common voltage regulators. This results in a low signal on the inhibit input, typically disabling the voltage regulators. In all other operation modes, the pin INH is actively pulled to battery voltage, enabling the external voltage regulators. The load resistance at the pin in shall not be lower than 10 kilo ohm. For 12 volt battery systems, if the pin is not used for voltage regulator control, it can be left open. For applications, it is recommended not to drive more than about 1 milliampere out of the inhibit pin. So then maybe for now, we make a text here. believe. Yeah, figure out the supply. Something like that. Just so I know to come back to it. Either via the bus or via the wake pin. Detection of a wake up event. The wake up flag is set and signaled at RxD and ERRN. So I wake. So 12 volts divided by 15 milliampere. .8. Yep. So if it's 1 kilo, it should be good then. Or yeah, of course. Do they say here 40, assuming that VBAT will not exceed 40 volt DC? 40 divided by, yeah, so it should have at least 3K. But we don't. We're just gonna assume that it has 12 volts max anyways. Of course it can go higher than that, but we're not gonna hook it up to a car battery anyway, so. But if you were to do that, yes, then you need to do this. Because 40 divided by 0.8 would be 50 milliampere. Yeah. 40 divided by 850. Yeah. That wouldn't be enough. Typical value is 20 kilo ohm with a maximum pull down, pull up current of 10 microampere and the maximum threshold of typical value is 20 kilo ohm, then we go for 20 kilo ohm. And we can also calculate that, I guess. RS, what was that? That's this one. So this relationship has to be less than VBAT minus VBAT. Which we assume to be 12 volts, more than that. Threshold voltage, so 9.5. Oh, max 10 then. I pull. So if it's 150 or 151 times 10, so wait, 151K times 10 . wouldn't that be? $1.5 volt, which is less than that. And then it can go down to 20. 21 times 10. Oh, what am I doing? I'm too tired for this. Hey, what's up? I see I have some viewers. How are you doing? Thank you for joining. Oops. Clicking around there. Fun to see that we got some viewers. Wake up flag. Do I need to do that or deal with that really right now? Bus failure diagnosis. I want to read into this though, a bit more later. How to read the bus failure flag, for example. Bus fail diagnosis is very important. Following bus failure conditions are detectable by the transceiver. Can high listed short circuits are detected in the range of 0 to 50 ohm short circuit resistance. Yeah, anyways, that we can take a bit later. For now, we're just bringing up the circuit. And a voltage detection. Oh, we're already getting tired and I haven't streamed for 50 minutes. The VCC supply must be able to deliver current of 65 milliampere on average for the transceiver. Typically, a capacitor between 47 nanofarad and 100 nanofarad is recommended being connected. So this is to the 5 volts, if I'm not mistaken. Damn, okay, so this is page 71. Where was the... Here? Right. 48 and 71. So we need the 5 volt. I don't like this at all. Not one bit. I will do like this. And make a label for con wake. So uh, so down here to filter, down here to this. No, so looks better like this, although not perfect. Uh, Yeah, the selection of some of these components might be a little bit intricate than just reading through the application diagram or the application note. But for the time being, we're just gonna select something. Now we can optimize. So it says, depending on regulation capabilities of the used voltage regulator, the bypass capacitor may be much smaller. And the extra current demand in the case of bus failures can be calculated. So I guess in the event of short circuit from CAN high to ground, the bus is clamped to the recessive state, and according to the CAN protocol, the microcontroller transmits 17 it's blah blah blah. Yeah, so in the case of that, it needs to supply, and therefore we need to have enough storage, energy storage. Again, we just select micro, and micro. EIO. Got a lot of rails here now. We'll have a LIN interface, a CON interface. This we can maybe split up into different blocks when I think about it. Like a network. Can you have another page in? It's not. LIN bus go to the connector. Same with the CON. Or the connectors. Thank you so much for stopping by to the stream. Hope you enjoy this content. Please write in the chat if you have any questions, if you want to discuss or talk about what you're seeing, or talk about anything else for that matter. Really fun to have people to talk to about what we're building here at Develop the Potential. Or engineering blank electronics. Today we're engineering automotive electronics. We'll do that the upcoming weeks, probably whole February. We'll be working on this every day for 1 or 2 hours. And it will be very exciting. Automotive electronics is actually really cool, I have to admit. And you'll have a chance to participate into the design of this component as well, in terms of what type of functions it will have. Actually, all the components will make in the automotive field, whether it's sensors or controllers or, I don't know, HMI, human, what is it? HMI, human interface? Like it can be displays or buttons. Yeah, whatever it is. Cool to have some participation and yeah, create some electronics for the world. My ambition is to start my own company and create a lot more electronics. And right now, this is what I can do after work, after hours, a little bit late night designs, PCB, schematic PCB you know, simulations, prototyping. We'll order these parts too when we're finished, and we'll do some software development. Probably order some NXP S32Ks, some dev boards or something to try out different communication protocols, CAN interface, LIN interface, Ethernet, and serial interfaces. See if we can create an automotive network architecture that we can play around with. We can basically place these components around the room and send commands to different boxes or nodes in this room and test them out. Very excited to do that. So, wow, 3 viewers. Great to have you here. Very cool to have you here. And I'll do my best to do some cool designs, at least. I have a lot to learn. But I figured, you know, if you want to be better at something, you just have to go for it. Have some discipline. It helps that you're dedicated and that you're passionate about what you're doing. And in this case, I'm passionate about it. For real. This is what I think I'm good at. And I still have tons to learn. Tons. Oh, really in my body, I'm getting tired. Anyways, let's have another look at our design. Let's continue. Interface pins. When applied signals at TXD show very fast slopes, it may cause a degradation of EMC performance, depending on the OEM. An optimal series resistor of up to 1 kilo ohm within the TXD line between transceiver and microcontroller might be useful. Along with pin capacitance, this would help smooth edges for some degree for high bus speeds close to 1 megabit per second. Additional delay within TXD has been taken into account. And here we can just add a resistor, I think. Like this. And then we also make a CON or MCU TXT like that. I just do like TXT on this side too. Remember to put in some labels, so I don't have to go over and do it on everything later. Da-da-da. And I should make a comment about that EMC. .75. So we know that because of fast slopes, we add some damping to not have problems with EMC. I think that's pretty logical. But it's very important in the automotive industry. As with pin TXT, a series resistor of up to 1 kilo ohm can be used to smooth the edges of bit transitions. I'm usually way more like I will edit the symbols so that everything is lined up perfectly, and I can, you know, have all my power stuff here, all the stuff going to the MCU that way, the bus this way, or vice versa. Yeah, it's a bit messy right now. Same here then. Can add another EMC. MCU RXD con. You know, doing electronics design, schematic design, it's like art, you know? I mean, it really is. It's like you're trying to tell a story. Mode control pins, they are typically directly connected to an output port pin of a microcontroller. So, oops, MCU enable. It's a bit long, these labels, but can fix that later. So this one we leave now, not connected for now. Do we figure the supply? So if we use this inhibit pin to to turn on the voltage regulators. These. So right to the enable pin or something. Idea here with using hierarchical modules is that we can reuse this. Well, we'll go into detail on the CAN interface and make sure we select components exactly how they should be, so we know that they will work flawless, at least for a hobbyist design. And then also do some considerations when it comes to automotive and real applications, but we'll simplify it. But we're still gonna select components so we know that this circuit works. But just to get it on paper and see what you have to work with, everything gets a lot easier. So yeah, we got the bus pins. Instead of a one resistor termination, it's highly recommended using the so-called split termination, illustrated in figure 44. Two resistors of 60 or 62 ohm. Also available at the center tap of the termination is terminated to ground via a capacitor. It's in this range. So the symmetry is crucial for emission performance of the system. The matching tolerance of the two terminator resistors should be as low as possible. Desired less than 1% tolerance on these resistors. Additionally, it's recommended to load the CAN high, CAN low pin each with a capacitor of about 100 picofarad close to the connector of the ECU. The main reason is to increase the robustness to automotive transients and ESD. Here it should also be as low tolerance as possible. Yeah, here's the termination concept. So we'll be a master node, so we'll... Do we need to terminate then? PCB checklist. Maximum bus line length. Okay. So the termination resistor is 60 ohm. Okay, so we also got the split. I forgot to read about that, but basically we'll have, okay, how to do this clean. Need some resistors here. So that and here. That to ground. So actually I'll do it here. How much was this? Between 47 and or 4.7 and 47. Just do 47 now. So and then 100 picofarad. Oh, of course. Oh my god. What is going on here? Oh. So I think think I will call it a day. Actually, with that, so then we can con high. Right, out bi-directional, and I con low. Excellent. Something like that. It's not perfect, but at least we lined up everything. Put in the components that is advised through the application notes and the data sheets. More than that, we don't really know, right? We can't know everything till we have put it on the sheet or on the schematic. So I think that's a good start. What I can do for fun is sync. Damn. Yeah. Enable this, con high, con low, this, and oh boy. There you go. I like doing like this. And I mean, you will never really expect to have a complex design unless you're doing something ridiculously simple. So why not use these blocks and modularize your design so you can reuse blocks of schematics that you know work, that you know works. You can test it. You can change it, test it again, improve on it, but you have ready to go design blocks. Okay. Hey, Moldark. How you doing? Thank you so much, guys, for watching the stream. I got 5 viewers. Never had 5 viewers at a time. That's awesome. Hope you're doing good. Hoping all is well where you are in the world. Please put a like on the stream if you enjoy it. Subscribe to the channel. I'll be here tomorrow again around the same time probably. So yeah, nothing more to say really. I think I will log off, get some good night's sleep, go to work tomorrow, and get back here. That's what I'm looking forward to, actually. I mean, and I enjoy my work, but I enjoy more building stuff on my own, be my own boss, and have some people come in and have a good time with me. Chill and relax and do some electronics. Talk about whatever you want to talk about. Okay, that's it. Thank you for watching. Until next time. Ciao.